Okay, here we go. All right, it's the 21st of July. A couple more review ideas from logarithms. The first one is exponential functions and logarithms undo each other. So for example, if I want to solve 5 to the x equals 125, I can use the verbal approach, which is x is the power that goes on 5 to get 125, which allows me to rewrite it as x equals the power, and so I use the log symbol that goes on 5, so use base 5 to get 125. That is the answer. If you have Desmos or another decent calculator, you can figure out that that is 3. X equals 3. As another example, let's see. I use 10 because I know that power. Know that 10 equals log base 2 of x. Is the power that goes on 2 to give x. And so now I can rewrite that using the exponential form. 10 is the power that goes on 2, which is 2 to the 10th, to get x. And if you have a calculator, you can determine that's 1024 equals x. This is the verbal way to solve these. It always works. It's the verbal mathematics. There's a kind of shortcut to approach this, which is the purely symbolic way. So we've got, well, we had 5 to the x equals 125. Now, since logarithms undo exponentials, I'm going to take the logarithm of both sides. If this first equation is true, then the second equation is true. All right, I took 5 to the x and I stuck it into a log base 5. I took 125 and I stuck it into a log base 5. Take a minute and watch the pen, because we need the time dimension here. Log base 5 of 5 to the x, that cancels and just leaves what's in the exponent. And boom, that's the same thing I got when I used the verbal process to rewrite it. All right, the log base 5 of 5 to a power cancels the 5 part and just leaves the power, just leaves the exponent. And the other one was 10 equals log base 2 of x. And because exponentials undo logarithms, I can put each of those up in the power. Since the first equation is true, the second equation is true. And again, take a minute just to watch. The 2 and the log base 2 cancel, leaving me on the right side just that x. 2 to the 10th equals x. That's exactly what we had when we did it the other way. So that purely symbolic way is the same process as the verbal. It skips that verbal word. Especially if you take Math 111 with someone besides me, you're probably going to be doing it more this way than the verbal way. How is it? Is it okay? Is it readable?
Yeah.
Okay, good. All right. So now let's use this in a story. A population of honey badgers starts with 4 badgers. Every year, the population increases by 7%. I'm going to ask 2 questions. 1, how many badgers will there be in 10 years? I could ask another question, which is how many years will go by until there are about 200 badgers? So if we want to answer these questions, remember I laid out 4 steps. The first one is what kind of function? All right, what function is best going to model this situation? Anybody?
Exponential.
Exponential. Why did you say that, Scott?
Why?
Yeah,
Just because this just looks like some of the problems we've done in the previous.
that's great. Yep, that's a good reason. Absolutely. It looks like what we've been talking about, and we've been talking about exponentials. Yep, good. And the reason these are exponentials is because it's a constant percentage change. It's a percentage change question, not an addition subtraction question. Okay, so it's exponential. And so now we pick the function. What does the general function look like? F of x equals b times a to the x. What do the letters mean? That's our next step.
Initial.
B is the initial value. A is the multiplication factor, which we find from the percentage growth, but isn't exactly equal to the percentage growth, and x is years. And so now let's get that information in there. Find the values. B equals, we started with 4 badgers, so B equals 4. The annual growth rate is 0.07, so it's 1 plus 0.07 or 1.07. And so our function looks like f of x equals 4 times 1.07 to the x. So we've converted this verbal representation of population growth, which contains all the mathematical information we need. We converted that to a symbolic representation just because it tends to be a little quicker to work with a symbolic representation. Now we can answer question 1. How many badgers after 10 years? That was a question, right? Yep. So that's going to be f of 10, which is 4 times 1.07 to the 10th. Calculator. Four times 1.07 to the 10th. Okay, not a lot. 7.8, approximately 8 badgers. The second question, when will there be 200 badgers? Okay, so that means 200 is the output. And we don't know the years. So we want to solve this exponential equation.
Oh,
So when solving an exponential equation, I mentioned this. Step 1 is isolate the exponential using SADMAP, right? Using PEMDAS backwards. So I have 200 equals 4 times 1.07 to the x. I like to circle the exponential so I know when I'm isolating. In this case, it's pretty straightforward. I'm just going to divide both sides by 4. And I get 50 equals 1.07 to the x. X is trapped inside of an exponential. How do we undo an exponential?
square root.
Nope. Nope.
Take the log of it.
Yes. Exponentials and logarithms undo each other. If you've got an unknown variable trapped in an exponential, you use a logarithm to undo that, to unwrap it. There's our base, 1.07. So using the purely symbolic way, I can do log of 1.07 of 50 should equal log base 1.07 of 1.07 to the x. Since the first equation is true, the second equation is true. The log base 1.07 and the 1.07 cancel, leaving me just x on the right side. And then Desmos or some other highly capable calculator will figure this number out. So come over here. Desmos doesn't have a problem with using any kind of base. I know you can't see this. Log base 1.007 50 is 57.8 years. 57.8 equals x, so about 58 years. I'm gonna try to fix the auto again because it's giving me a headache. Ah, much better. Right, so we can use the unwrapping process when we are dealing with word questions as well. Now, I'm going to give you one extra, which is natural exponential and natural logarithm. Remember that E, which is about 2.718, is the natural exponential base. And instead of log base E, we write ln, natural log. So you deposit $100 in a savings account that has a continuous interest rate of 4% annually. Make a natural exponential model. All right, so step one is what kind of function do we use? Well, that's good. I said it right there, natural exponential model. So the formula for a natural exponential model is just a little bit different than for just any old exponential. We still have our initial value b, and our base now is not a, our base is e. That's a number, 2.718. And up here in our power, we have an r times x. So our job is to figure out what the letters b, e, r, and x represent. B is still the initial value. E is about 2.718, which is the natural exponential base, the base that can represent any growth. R is the interest rate as a decimal. And X is the number of years. So B was 100, E was 2.718, but we're going to leave it as E. R is 0.04 because it's a 4% interest. It's a different way of using your growth rate in an exponential model. Instead of doing 1 plus 0.04 as the base, we do E as the base and 0.04 as the exponent. And X is years. So our formula is f of X equals 100 times E to the 0.04X. How long? So let's ask how long until you have $180 if you're not doing any deposits or any withdrawals. So we're solving $180 should be 100 times e to the 0.04x. Just like with our honey badger question, we're gonna start by isolating the exponential, which is all of this. So let's divide both sides by 100. And we get 1.8 equals e to the 0.04x. And then the natural log undoes e. So using the purely symbolic way, we can say the natural log of 1.8 equals the natural log of e to the 0.04x. And the natural log and the natural exponential cancel, leaving us just what was in the exponent. And now let's SAD map for x. So you just divide both sides by 0.04. There's your answer, natural log of 1.8 over 0.04. That's how many years it will take. Do you have any clue about how many years that is?
Logs, you said 2.1 something's log, no.
Yeah, but I certainly can't look at that and
Oh,
say, right, like I can't look at that and say, well, that's 3 years, that's 40 years. I have no idea how big that is. And that's why we go to the calculator to get us a decimal. So grab Desmos. We're going to do natural log of 1.8. And I'm going to divide the whole thing by 0.04. And we get 14.7 years. That's how you use the natural log to unwrap a natural exponential. There's one other type of question that we can ask using, well, there's lots of questions, but there's one other type of question I want to talk about that uses the natural exponential formula. And that is suppose you invest $250 in a stock. 21 years later, it is worth I'm going to try to do a little mental arithmetic so I don't give you something totally unreasonable. Okay, $1,000. If the growth was continuous, this is a key word that should give you a hint to use the natural exponential. Especially with money. Anytime we talk about a continuous growth, think I'm going to use a natural exponential formula. If the growth was continuous, what was the interest rate? So again, we're going to start by going through our steps. If you use the steps every time, it'll be easier to get to the correct setup. We start by asking, what kind of function should I use to model this?
Quadratic?
No. Talking about a financial investment where the growth is continuous. What model have we used for this situation? We used it in the previous question. What's that? Natural exponential. It's a percentage growth and it's continuous. That's going to tell us to use a natural exponential. Right? Do you see why step one is actually super important? And it's not necessarily easy. Figuring out what function to use to model is a huge part of mathematics. So we're going to use an exponential because it's a percentage growth. And we're going to use a natural exponential because it's continuous percentage growth. So the next step is to write down what that function looks like. F of x is b times e to the r times x. Where b is the initial value, which in this case is what? 250. E is the natural exponential base, which is about 2.7. But we're going to leave that as E because all of our calculators have the number E. But it can help us recognize, okay, that is a numerical base. R is the interest rate. Do we know the interest rate yet? No, in fact, I'm asking, what is this? So we're trying to find this. X is a number of years. And do we know the number of years?
21 years.
Exactly, 21. So what I've got is I've got f of x. Oh, that's the output, right? This is the dollars, the dollars, right? And in year 21, f of 21 was $1,000. So I actually have a lot of information. I'm only missing one piece. So put that into my formula. I have 1,000 should be my initial value, 250 times E raised to the R times 21. And I'm trying to solve for R. The process is going to be the exact same as the previous question when we solve for X. Just instead of solving for the number of years, we're solving for the interest rate. I'm going to hop through this a little more quickly. Divide both sides by 250. And we get 4 equals E to the R times 21. I can use the natural log of both sides, which cancels the natural exponential. And I'll switch the R and the 21 so it looks more like the multiplication we normally do. So I have natural log of 4 equals 21R. So natural log of 4 divided by 21 equals R. And if I'm moving too fast, I'm doing it on purpose because I want you to have to work through this on your own. Natural log of 4, all divided by 21, about 6.6. Or sorry, 0.066 or 6.6%. And now you can make some other financial decisions, like what if I keep that money in there for another 10 years? What's it going to be worth? Or what if I tripled my initial investment? What's it going to be worth? Okay. We got to switch over to chapter 4 now. may talk a little bit longer than I would have otherwise, but we'll definitely come back to chapter 4 on Wednesday. Polynomials and quadratic expressions. Okay, we're going to start with multiplying and factoring. I'm just going to start with an example. Multiply out the expression 2x times x squared plus 7. All right, so this multiply out the expression means write without parentheses, which is a little, I think, ironic that I put that inside of parentheses. Now perhaps many of you have done this, perhaps you have a system. If you want to use that system, that's totally fine. I'm going to build a system for you if you haven't used it. And also it's going to be really helpful when you get to factoring. So I use what's called the box method. And you put one factor on the left of a box, one factor on top, and multiply to fill the box. So let me show you what I mean. I've got 2x, that's going to go on the left of my box. And I've got an x squared plus 7, that's going to go on the top of the box. And I'm going to split the box every time I see a plus or a minus. And then I'm going to do all these little multiplications one by one. 2x times x squared is 2x cubed. All right, that comes from our rules of exponents. X times x squared is x cubed. And then the 2 just is still there. And 2x times 7 becomes 14x. Now you just add or subtract the terms in the box. 2x cubed plus 14x. There we go. That's our answer. That is the exact same expression as 2x times the quantity x squared plus 7. I started with a relatively simple one, but this works for even very complex expressions. So let me give you a more complex one. Example, multiply out negative 3x to the fourth minus 5x times 2x cubed plus 7x minus 4. Hopefully that'll do. Trying to use all different numbers. So I'm going to build a box. I'm going to put the first term on the left side of the box, which is minus 3x to the fourth minus 5x. And I'm gonna put the second term on top of the box, which is 2x cubed plus 7x minus 4. And I'm just gonna divide the box at every plus or minus. I'm gonna end up with 6 cells in this box. Notice there's 2 pieces in the first term and 3 pieces in the next term. 2 times 3 is 6. Right, we're just basically making this a 2-dimensional question instead of a 1-dimensional question. And now I do my multiplication in each of the little cells. Minus 3x to the 4th times 2x cubed. Well, the x to the 4th times the x to the cube gives me an x to the 7, because 4 plus 3 is 7. Minus 3 times positive 2 gives me a negative 6. Then I move on. Minus 3x to the 4th times 7x is going to be minus 21x to the 5th. Minus 3x to the 4th times minus 4 gives me positive 12x to the 4th. And then minus 5x times 2x cubed gives me negative 10x to the 4th. Minus 5x times 7x gives me negative 35x squared. And minus 5x times minus 4 gives me positive 20x. May not be the fastest way, but what I like about it is it's methodical. If you do each piece separately and then you put them back together, I think with practice, you're less likely to make mistakes than if you just try to do it in one go. And I make a lot of mistakes when I do math. You've all seen this. Not a big deal if you're just doing it in your head and it's just for fun. But if you're doing something important, like working on a project or trying to get a good grade, it's worth doing it systematically, even if it feels like it takes longer. So now that we have our box filled out, now we add or subtract the terms in the box. And that just means putting them one after the other. I had a minus 6x to the 7, minus 21x to the 5th, plus 12x to the 4th, minus 10x to the 4th, minus 35x squared, plus 20x.
And versus foiling it makes you don't get so
Listen,
screwed up.
yeah,
Right.
it's a version of foiling. It's
But
a more
keeps it all together.
systematic, yeah. I just consider it to be a more systematic version
Okay.
of foiling.
Makes sense.
And it works well when you have just the 2 and 2, especially when you want to factor. I like the box method. So notice you have 2 terms here with the same x power. So you can combine those terms. And so I would end up with minus 6x to the 7, minus 21x to the 5th, plus 12 minus 10 gives me plus 2x to the 4th, minus 35x squared, plus 20x. Still easy to make mistakes. I almost made a mistake here. I said 35 and I wrote 3 and I had to fix that.
What if you have 4 terms up on the right side?
You just keep making your box bigger and bigger.
Okay.
Your box is going to have a column for each term here and a row for each term here. And this is the way a computer would do it too, actually, right? If you were actually asking the computer to multiply a 10-term thing times a 37-term thing, the computer would make a box that's 10 by 37, do them all, put them all together. And we have successfully multiplied that out. And then the question, of course, is, but why would I do that? I mean, other than practice, because there are times when you want to multiply it out, a lot of times, and I can't necessarily help this, on a homework, you're going to say simplify. Well, I don't necessarily think this is simpler than that. It's just another way of writing it.
Really?
Okay. This way, it's easier to see that the largest power is an x to the 7, right?
Right.
So that's one way in which it's useful. Okay, so that's that. That can also help you take care of all the negatives that can float around. So let's jump over to factoring. We're gonna talk about two ways of doing it. We're gonna talk about the greatest common factor. And we're gonna talk about factoring quadratics using the box method. And again, there are other methods of doing it. If you have another method that works for you, that's fine. If you don't, or if that method has never really felt solid, then I recommend the box method, because I do find it, after a number of years of teaching, that's the easiest way for me to explain the concepts. But first, let's start with the greatest common factor. Which is going to generally be abbreviated to GCF. What is the GCF of 172? What is the largest number that divides both 100 and 72? GCF is the largest number that divides both. In fact, I could say, what's the GCF of 3 numbers or 19 numbers or however many? Now, I have a process for doing this that I find works pretty well and translates well to when we start using variables. And the step one is just to write the complete factorization of each number. I'll show you what that means. 100. Can I write 100 as the product of two numbers? What numbers are those? 50 and fantastic. That's 2 times 50. Can I factor this more? 2 is going to stay by itself, right? 2 is prime, no more factor in there. But can I split 50 into different factors? What could I write 50 as? Exactly. So I have the first 2, and now I have the second 2 times 25. Can I divide 25? 5 times 5. 2 times 2 times 5 times 5. This is the complete factorization. A 100 is equal to 2 times 2 times 5 times 5. You might hear this as the prime factorization because 2 and 5 are both prime numbers. Now let's do it for the second number. There's also a process if you're not sure. First thing I would say is this number even? 72? Yeah, well, that means I can write it as 2 times, I divide 72 by 2, 36. 36 is even. So I can write that as 2 times 2 times 18. All right, you just keep trying numbers. 18 is even, so that's 2 times 2 times 2 times 9. And 9 can be divided into 3. That's the complete factorization of 72. 2 times 2 times 2 times 3 times 3. You may get there a different route, that's fine, but a fail-safe is to say, can I divide it by 2? And if you can, do that. And if you can't, then say, can divide it by 3? And if you can, do that. And that's what the calculator says. Let's take just as an example. Let's say I have 298.47. Okay. So I'm trying to factor this. So I divide it by 2. That doesn't work. Aha, divides by 3. That's not going to divide by 2 because it already didn't divide by 2. Does that divide by 2? No, it doesn't divide by 3. Probably doesn't divide by 5.
Odd number.
Divide by 7. No. How about 11? No. All right, you just work your way up. And eventually, let's see, 13, 17, 19. I'm trying all the prime numbers. Right, it's not super fast, but it'll get you there. Right, you can do it. I'm never going to give you a question where I ask you to factor a 5-digit number. That's silly, but it's possible. Okay, so that was step one, is to write the complete factorizations. And step two, just find common factors. So 100 was 2 times 2 times 5 times 5. And 72 is 2 times 2 times 2 times 3 times 3. And I'm just going to circle any number that appears in both. There and there. 5 appears in the 100. Does it appear in the 72? Nope. So it doesn't appear in both. 3 does not appear in both. And that extra 2, it's got no partner. So I'm not going to circle it. And step 3, split each number into the greatest common factor and the rest. So 100, I'm going to rewrite this just so you can see the process a little more statically, but normally I would just go from here. Since those match, that's 2 times 2, which is 4. On the top, I get 25, and on the bottom, 2 times 3 times 3, I get 18. Okay. And there we go. The greatest common factor is 4. So that's the biggest number that divides both of them. All right, so when is this helpful in algebra, which is what we're doing? Now, I think it's helpful also when working with numbers. This is a branch of mathematics called number theory. This is the base of this, but this concept right here of completely factoring some of the deepest, most complex mathematics ever developed just comes out of this idea. The hardest mathematical proof I ever did related to this concept right here, which is something I really think is interesting about math, is the same topic can have really basic, clear, understandable things and really obscure, challenging, almost mystical ideas. So let's factor, let's see, 28x to the 5th minus 35x cubed plus 16x squared using the greatest common factor. And we're going to use the exact same steps. Step 1, write the complete factorization of each. These are no longer numbers, they're terms, but the idea is the same. So 28x to the 5th. 28 can be factored. It's even, so I could divide it by 2. What's 28 divided by 2? 14. And 14 is even, so I can also divide 14 by 2. All right, so I get 2 times 2 times 7, and that's as far as I can go because 7 is prime and 2 is prime. And then I have 5 x's. And for now, I'm just going to actually write all 5 of those x's, because it's going to help me when I match. And I do the same here. I've got negative 35x cubed So I like to put the negative so I don't forget it, just in a parentheses by itself. You don't have to, as long as you can remember there's a negative, you're gonna be okay. 35. Can't divide it by 2. Can I divide 35 by 3?
No,
Nope. By 5?
yep.
Yes, okay. 35 is 5 times.
Okay.
And if you don't know that, you grab your calculator, you do 35 divided by 5, and it'll tell you. And that's it. 5 and 7 are both primes. So now I've got my 3 x's. And then I have a 16x squared. Well, 16 is 4 times 4, or 2 times 2 times 2 times 2. And then 2 x's. Now I circle any factor that shows up in all the terms. Oh, the terms. So let's take a look. I've got a 2 in the first term. I have a 2 in the third term, but is there a 2 in the middle one? So I can't circle it. Are there any numbers that show up in all of them? Nope. Not really what I wanted. I kind of goofed that up, but we're going to roll with it. So none of these numbers are common. That's okay. How about variables? I have an x in all of them, so I'm going to circle those. I have another x in all of them, so I'm going to circle those. And while the first 2 terms still have x's, there's nothing in the last one, so I can't circle that anymore. So step 3, split each term into the greatest common factor and the rest. 28x to the 5th is equal to 28, sorry, the greatest common factor is x squared, and then 28x cubed, right? That's the rest. Minus 35x cubed is going to be x squared times minus 35x. And 16x squared is going to be x squared and 16. So what's the greatest common factor of this polynomial? It's the largest term that shows up in all of them.
X squared.
Yep, there's the x squared that shows up in all of them. And the rest doesn't have any commonality anymore. So last step, write as a polynomial. I have an x squared. That's my greatest common factor. And then I open a parentheses and I just list the other terms one after another. 28x cubed minus 35x plus 16. And I've done my greatest common factor. Let me see. All right, I'm going to go in a little bit longer today, Gabe, because I did a little bit of a recap. I'll go for another 10 to 15 minutes. And then we'll get started on the worksheet. So that's how you do greatest common factor. If I had really put a little more brain power into it, I would have had a number that showed up in all of them as well, but you'll get practice with that. Okay. Factoring quadratics using the box method. So first of all, what is a quadratic? A quadratic is a polynomial with x squared as the largest power. Now, I haven't gone into a deep review of what polynomials are. I'm kind of just assuming that you're coming in with that basic knowledge, but if you need to do a review, Gabe and I are here. So for example, a quadratic might be x squared plus 5x plus 10. Sure. I don't like that one, but change the 10 to a 6, please. X squared plus 5x plus 6. Or it could be minus x squared minus 4x minus minus 3. I think I'm okay with that one. Yeah. Or it could be something like 3x squared minus 6x minus 24. These are all polynomials where the largest power is an x squared. And it's traditional to write your polynomials with the largest power first and then work your way down from there. If you ever see it not written in this order, the first thing to do is write it in that order. So when I'm looking at this, if I want to factor it, there are definitely not going to be any common, well, this one has a common factor. The 3 is a common factor. But the first two, it's not like there's an x in all of the terms, right? So there's limited I can do with the greatest common factor approach. So the box method is how we generally factor quadratics. Before we get to factoring quadratics, let's just really quick multiply out the quadratic x plus 3 times x plus 2 using the box method. So I'm going to build a box. I have x plus 3 on the left side and x plus 2 at the top. And I divide my box whenever I have an x or whenever I have a plus or minus. So I end up with a window pane, a 2x2 box. And then I multiply each piece separately. What's x times x?
X squared.
X squared, cool. What's x times 2? 2x, right? The multiplication is fairly straightforward, which is nice. X times 3 is 3x. And what's 3 times 2? 6. So I get x squared plus 2x plus 3x plus 6. And notice I have a 2x and a 3x. That's the same power. So I can write it as x squared plus 5x plus 6. I'm going to redraw my box. The lower right pane is the two constant terms multiplied. The two numbers multiplied. And these two diagonal panes, they add to the sum of the numbers. The lower right hand is the product of the two numbers, and the two diagonal panes add to be the sum of the two numbers. So that means if I start with x squared plus 5x plus 6, and I want to build the box backwards, the first pane is always x squared. This lower right pane is the product of those two numbers. It's going to be the 6. And I don't know what these two numbers are yet, but I know that they multiply to equal 6. So what I'm going to do is I'm going to take all the factorizations of 6, all the ways you can multiply two numbers to equal 6. What's one way I can multiply two numbers to equal 6?
Right.
2 times 3, 2 and 3. What's another way?
1, 6,
1 and 6. Are there any others?
negative. I'm trying to-
Very good. I could have -2 and -3. And I could have -1 and -6. These are all the factorizations of 6 using integers. As soon as we get into fractions, I don't do that. I don't do that. I'm not going to teach you that. I use Desmos. I put it in a graph. I use a visual analysis. This is a very numerical and symbolic way of factoring. There's no reason why you can't use a purely graphical method as well. So on Wednesday, I'll show you that. All right, so these are all the possible factorizations. And I know that if I add these two numbers together, they should equal 5. So I just check. One of these works, the others don't. So I circle the one that works. And that means there's a 2x here and a 3x there, which means that must be a +2 and that must be a +3. And now I can write it in factored form. All right, let me do the other two examples. Let's factor -x squared minus 4x minus 3. My advice is never factor anything unless it just has a plain old x squared, because it gets more complicated. So step 1 is factor out the negative. Minus x squared, -4x will become a +4x, and -3 would become a +3. All right, -x squared minus 4x minus 3. And now we'll do the box method on the inside. I have let's see, an x plus and an x plus. That'll be the x squared there. The lower right is going to be the 3. I'm going to look for two integers that multiply to equal 3.
1 and 3.
1 and 3 and -1, -3. There aren't any others. So I test, I add them together, and one of that set works and the other set doesn't work. I want my two numbers to add to equal 4. So that must be an x here and a 3x there. I factored it. Step 3. Don't forget the negative. This is the most common mistake I see, is you get the negative out and then you forget that it still exists, but it does still exist. So put that negative in front and then write your two factors. And you're done. All right, one more. And it's similar, because we're gonna do a factoring and then do the box method on the inside. We have 3x squared minus 6x minus 24, and let's hope I did my mental arithmetic correctly. So the first thing is I don't like that leading coefficient. I don't like that 3. So I'm going to factor it out. I'm going to write it as 3 times x squared minus 2x minus 8. And if I really want to be smart about it, I'm going to go down here and I'm going to build that right away so I don't forget the 3. And just leave myself a gap to do the box method. Right? That's, I think, the best way to avoid forgetting the leading coefficient is as soon as you factor it out, get it right down there at your answer level. And so we'll do the box method. I got a box here. I have x's there. So I have an x squared in here. What's going to go in the lower right hand? Minus 8. Yeah, because there's a negative. So let me come over here and do some work on the right. I need two numbers that multiply to equal negative 8. Minus 4 and 2, or 4 and minus 2. Yeah.
Gives you 1 and minus.
Minus 1 and 8, or 1 and minus 8. And that's the only pairs of numbers. And these pairs of numbers have to add up to equal negative 2. So I test them. And I get Scott's jumping to the first answer each time, but that's not necessarily. Sometimes it's going to be the third option or the ninth option or whatever. 2, 7, negative 7. So I'm looking for the pair of numbers that add to equal negative 2. It's right here. So I must have a minus 4x there and a 2x here, which means I have an x minus 4 on the top and an x plus 2 along the left. And that tells me my factors are x plus 2 and x minus 4. With the 3, which I couldn't forget because I wrote it before I did anything else. And that's how you do the box method. If ever you run into a box method where your constant is a fraction, I say, don't use a box method. Use the tool that works best. And there are better tools when working with fractions. It's possible to use a box method. Gabe, you may learn like the diamond method or something that's similar to that, where you can do it with a fraction, you can do it with different leading coefficients, but I don't like it. Where's that other, there's some sort of like,
Quadratic formula.
yeah, but there's something in the textbook, but I forget what it's called.
You see that?
Quadratic formula always works. That's another tool. Yeah. Okay. Although I got a couple of students, but I'm still going to take the midterm, so I'm not going to hand it back until Wednesday. If you are still working on the logarithms worksheet, that's totally fine. Here's the one for today. Yeah. There's a lot more in here than what we covered today, so we'll come back and finish it on Wednesday. So how far should you work? If you find yourself getting through question 3, all right, so they're multi-part questions. If you get through the end of question 3, you can stop there. And I'm going to give you one while I work on the key. I'll put the notes here. Let me